In this video I want to talk about graphs and graphing, and we're going to go way back. We're going to start pretty basic on this and move up to where I think you need to be in order to really be able to understand and interpret graphs properly. So we'll go way back, but before we do that, what I want to do is tell you that when I look at a graph, I look at the graph in two different ways. The first way I think about a graph is maybe as a table. Okay, so here we have a table of values, and so we have an x value and a function value. So our function gives us a y value that tells us if I plug in x into this function, what is my y value, what does the function do to it to get my y value. So whatever it is that we're doing, and happens to be squaring the x value, so suppose I go to -2 and I square -2, okay, I'm going to get +4. So if I go up from -2, I hit the graph right here at y equals +4. If I square +1, okay, I go straight up here, 1 squared is equal to +1, and I get my y value of 1, and so forth. So, you know, we're looking at this value, we're looking at this value. Obviously, we can do the same with the rest of these. So, in a way, a graph is kind of like a table. Find an x value, okay, it doesn't even have to be anything in a physical table. Let's look at, you know, x equals 1.5, for example, and we'll go up here and we hit the graph somewhere around here. And we say, okay, that corresponds to a y value right about here. If we plug this into a calculator and square it, we're going to get 2.25. And that looks pretty reasonable for what we've got drawn on the graph here. The other way I think about graphs is just as a picture that tells us something about how this function behaves. In other words, the graph of f of x equals x squared has certain characteristics to us that tell us a lot about what this function is doing for us. And so in that case, I'm not even going to worry about this table. Okay, I'm going to really just look at this picture for what it is. So what kinds of things can I tell about this from the picture? Well, I can tell that this is the lowest point. In other words, the y value is 0. That's as small as the y value gets. So I know it has a minimum of y equals 0, and that happens at x equals 0. I also know that this graph is decreasing. Now remember, we read graphs from left to right. So if I start out here in the left, I'm actually up here on the graph, and as I move from left to right, I'm going to be tracing along this graph, and I can see that my graph, my y values are decreasing along that interval, okay, from way out at -infinity all the way up to here. And I already said that at 0 right here I had a minimum point, okay, and so now from the minimum point we're going to start increasing. So my y values now are going up, 2, 3, 4, and so on. So just by looking at this graph, I can tell certain things about that. Where is it decreasing? Where is it increasing? What's the minimum value? Maybe a maximum value for some kinds of graphs. This graph happens to be curved everywhere. There's no straight lines. What does that tell me about what this graph is representing, and so on? So those are some things that I can tell from looking at the picture. Okay, so let's see how the graph itself relates to both of those interpretations. I want to start with a number line, okay? That is not what I wanted, so let's try this again. There we go. I'm going to just call these x values. Now, when we think about a number line, we think back to first or second grade, and we didn't really know about x back then, but I'm assuming at this point, hopefully you do know. X is just going to represent any of these numbers on here. And so the number line itself tells us about the relationship between these numbers. As we move from left to right, we see that our numbers get bigger. Okay, we can see which numbers are bigger than other numbers by looking at something like 8 is to the right of 4, and therefore 8 is greater than 4, and so on. We can also think about operations, for example, addition. Suppose we have 3 plus 2, and we want to figure out what that is. So what we're going to do is we're going to start at 3, and we're going to move a distance of 1, 2 to the right. So this is plus 2, and where do we end up? We end up at 5. Even subtraction, okay, works the same way. If I start at 7, and I want 7 minus 4, let's say, okay, I'm going to start at 7, and I'm going to go 1, 2, 3, 4 to the left, which is indicated by my subtraction, my negative sign, and that gives me a destination, a final value of +3. Okay, well that's all very exciting, but we want to move to something a little bit more advanced. So suppose that we take advantage of this thing we're calling x, and we say, all right, what we're going to do is figure out how we can add 2 to any number, not just 3. And so we said, let's just replace 3 with x, and x will be some number we'll fill in later. And we get x plus 2 equals what? Well, how do we work that out? Well, we choose a value for x, any number that we want on our number line, and we add 2. And adding 2 is the operation of moving to the right by 2 places. So if we were to then say, what is 6 plus 2? We start at 6, we move 2, and we get 8. And if we wanted to know what 0 plus 2 is, we would start at 0, move 2 to the right, we would end up at 2, and so forth. And so we see that as we change the value of x, we get different values for our result. And we just call that y in algebra. Okay, so we say that our y value then depends on x, and we get the y value from adding 2 to x. The problem that we really have here is that in order to find different values of y for different values of x, we have to I don't know, we can move our little window here, we can calculate a table, make a bunch of different numbers, but that gets very tedious, especially when we want to calculate y for a whole lot of values of x. In fact, what if we wanted to know what y was for every value of x? And so that's where we need to change our picture here in order to relate x, which we're starting with here, and y, which is our new variable that we've introduced, which is the result of some operation. So what I'm going to do is introduce a new number line, and I'm just going to copy this one. And let's go ahead and put it down here. And we're going to call this one our y. And so what we could do then is say, okay, if we have y equals x plus 2 like we did before, suppose I pick x equals 1, then we know that if we move 2 to the right, we get 3. And if I pick x equals 2, we're going to get x equals 4, or y equals 4 rather. If we pick x equals 3, we'll get y equals 5, and so forth. Problem is, these are separate sets of data, and it doesn't really tell me much about what happens if x is specifically 1. Which one of these came from x equals 1? And unless I keep track of it somehow, maybe make different marks or different colors, and that obviously is going to get very tedious very quickly. And so what I'm going to do is, let's just go ahead and move this down here a little bit. And I'm going to go ahead and introduce my other line here. And I'm going to rotate this and then move it. And let's just go ahead and recenter everything a little bit. That looks a little bit better. All right, so now what I'm going to do is I'm going to call this my y output. Okay. And now what I can see is that if I want y equals x plus 2, if x equals 1, I know that y is going to equal 3. Now I still have this situation where, and let's just do like x equals 2 and y equals 4. I still have the situation where I have a connection between these two, but as soon as I go on and plot something else, I sort of lose that connection. But if I do this one at a time and say when x is 1, y is 3, and instead of putting the points on the number line, I put it out here on what we call the coordinate plane. And I do the same thing with 2. I say when 2 is my x value, my y value is 4, and that gives me this point right here. When my x value is 3, my y value is going to be 5. When my x value is 4, I'm going to get a y value of 6. When my x value is 0, I get a y value of 2, and so forth. And so let's just go ahead and erase these guys here. And in fact, I'll erase my lines. And I'm erasing more than I want to, but you still get the basic idea here. All right, so what we're doing now is we see that now we get a pictorial representation. And in fact, if I were to plot every single point, I had that point right here too. If I plotted every single value of x, all of these here and added 2, I would get y values and plotted points all the way along like this. And what this does, obviously, is draws a picture. And in fact, this draws a straight line for this function, and that's why we call this a linear function, because the graph that comes from this is a straight line. And so what this allows us to do is to make a picture of the relationship between every value of x and every value of y that comes out of the function here. And so this kind of leads us to the idea of domain and range. If I plug in some value for x, the first question is, does this actually make sense? Does it give me some value of y? And for this function, it does. No matter what value of x I pick, there's always a number that's going to be 2 greater than that number, whether it's positive, negative, 0, or whatever. And so my domain in this case is all the possible x values, which is going to be the set of all real numbers. Okay? And similarly, any value of x that I plug in, all I'm doing is adding 2, and so my range is going to be also all real numbers. If I go back to this graph, I can see that I can plug in any value of x that I want, and even values along here where I'm marking that don't show up on the graph. I can imagine this graph continuing up off of the screen and continuing not just up but also to the right as I continue. Obviously, if I take the value 4 and square it, I get 16. It just happens that my graph doesn't go that high. However, even though I would say that the domain, okay, my x values here could be all real numbers, what do I get for a range? Well, when I plug in all of my possible x values, my y values are only going to be those values greater than or equal to 0. I can't get a negative y value from squaring x. So the graph can also tell you a lot about domain and range by just looking at what span of values left and right give me an output on my graph, and that gives me my domain, and what span of values up and down do I get from plugging those numbers in, which would give me my range. If my graph looked like this, when I talk about my x and my y values, what happens if x is positive 1? Okay, x equals 1. What happens here? Well, I don't have any y values. Whether I go up or down, I don't hit the graph, and so x equals 1 is not in my domain. In fact, my domain only includes, apparently, these values from x equals 2 out here to x equals 13. And so my domain could be written, not 0, 2 is less than or equal to x is less than or equal to 13, or I could say x is in the interval, or is an element of the interval from 2 to 13, and there's a lot of different ways I could write that. So my domain is limited to these x values, and so the only y values that I can get are the ones from those x values. Let me get rid of that little piece right there. Okay. So what are my y values? My y values seem to be, the lowest y value is right down here, so that's going to be y equals 1. And I have all these y values for all these different values of x that go up here to 1, 2, 3, 4, 5, 6, 7, y equals 8. And so my range would be, doing it again, 1 is less than or equal to y is less than or equal to 8. And so this would be my range, this would be my domain. Once again, I could picture this graph as possibly being a table. So if I have x equals 2, 3, 4, let's say, x equals 4, I got 1, 2, 3, 4, 5, 6, 7, about y equals 7.5, so I could start building a table that way. I can also look at this graph and draw some conclusions about things like its maximum value, its minimum value, where is it increasing, right here and right here, where is it decreasing, here and here, where is it curved up, where is it curved down, and so forth. So once again, the graph looking at x and y value relationship, sort of like a table, or looking at the big picture and seeing what the graph is doing.